Dr. Manuele Rusci received a PhD in electronic engineering from Università di Bologna on 2018. He is a postdoc researcher at the same university in the Department of Electrical, Electronic and Information Engineering, Guglielmo Marconi, and collaborates with Greenways Technologies. His main research interests include low-power AI-powered smart sensor and on-device continuous learning. Title of the presentation is Continual On-Device Learning on Multi-Core RISC-V Microcontrollers.
This one? Okay, thank you for the introduction. Actually, yeah, I must say that I've just moved to Q11 since 1 month, so I'm just, let's say, changing my affiliation. But by the way, the work that I will present today was mainly done when I was working at University of Bologna and Greenways Technologies. What I will talk about is some sort of topic which is also a little bit new, also in the machine learning community, which is the continual learning. And I will give you some sort of first studies that try to bring this sort of paradigm into the tiny space where we are, so tiny machine learning. So I guess now you're familiar, we are talking about smart sensors, so tiny device that consumes milliwatt and includes some sort of digital processing coupled with the sensing part. And we want to bring into this very little architecture some sort of complex algorithm. So the challenge here is that how can bring this complex algorithm like deep neural network into this. And so far we have been limited to, let's say, inference mainly. Let's say what I will refer to, especially in terms of platform, to bring this sort of complex algorithm, mainly refers to the type of microcontrollers. Here what I, let's say, target was some sort of modular architecture that has been introduced already in some other talks, where we have microcontrollers plus some other modules, and these modules are parallel clusters. So we can be flexible in the sense that we can activate the multi-core platform whenever we want to do some, let's say, also highly intensive mathematical workload, and still being flexible. And the flexibility is given by the fact that we are using general purpose architecture. So we have our instruction set to perform all of our instruction. Optionally, as is the case of RISC-V, we can, let's say, customize our instruction set in order to include some sort of DSP vectorial specific instruction, like this one, where we go for multiply and accumulate between 2 vectors of 8-bit values. So in a single instruction, we basically perform 4 MAC of a standard, let's say, multiply and accumulate dot product. So this type of architecture was actually built during a project, which is the PAL project, joint project by University of Bologna and ETH Zurich, but also, I mean, it's now commercially available, and Greenways is an example of it. Given this, we have been developing lots of actually software to bring deep neural network inference now on this type of architecture. So you see here from Deep Pseudocode that we took the module of the computation of the inference. Here we have a convolution, and the convolution you can see here that can be simply transposed into some sort of composition between transformation, like standard image to call and matrix multiply. This is pretty standard stuff. And let's say, thanks to our architecture, we can pretty accelerate this type of workload. And let's say, basically, we combine multiple tricks together. Parallelism first, by using this multi-core that we have available, the vectorial instructions as IMD. Plus, also, we make use of extensive data reuse. So as you can see here from the scheme, the matmul actually is spread between different cores and is computed among different blocks of the operands. So this one and this one. So this actually give us a pretty compact, let's say, code here, where I represent the assembly here, and you see that basically the main workload is computed by multiply and accumulate operation. That's why it's so efficient. And thanks to this, we could achieve a very high performance, let's say, 10 to 30 times faster than the standard state of the art. So we typically measure it in terms of Mach over cycles. The higher it is, the better it is. This led us to, let's say, achieve very nice results on this tiny microcontroller. So here is just an example where we have the combination of an SSD for object detection. So we were detecting license plate, and also we were reading after the detection the number of the license with a combined neural network. So this gives you the feeling already what is possible in terms of inference on these tiny devices, something that before was only possible in let's say, mobile type of processor like mobile phones or this kind of stuff. This was done using the principle that I showed you before and using some sort of tool set that has been also introduced before by other colleagues from Greenways Technologies. This actually was run at more than 1 FPS, and actually probably it was at the time, but I believe it still is the highest complexity which is possible in an MCU type of devices. Still, I mean, we were using some sort of, let's say, the software was making use of a complex pipeline to combine, to also exploit efficiently some external memory. So we were combining basically the software acceleration shown before with some other memories that shown coupled externally, but everything was basically quantized to 8 bits. And this is still, let's say, in a power envelope of 100 milliwatt in this case. Another example that I want to show you is just some demo that probably you saw already. So this is sort of denoising, audio denoising, where you have some noisy signal here, and you use some sort of neural network just to denoise. In this case, we were using some recurrent neural networks, but since it is not a classification, but rather a regression problem, the quantization was not that easy. So in this case, again, thanks to the instruction set, we were able to preserve the accuracy with respect to the floating point, mixing up together float 16 and int8 quantization. And again, this is possible thanks to the instruction set that we have, let's say, is possible to be customized by means of the architecture. And again, by using the multiple tricks of the parallelization, the optimized pipeline, we could achieve some sort of energy efficient gain with respect to other type of implementation that were extremely smaller than this. So this just to give you the feeling on what has been possible so far on the inference side. Let's say, whenever I did this type of work, let's say the typical design flow that we have followed was almost the same. So we were starting by collecting some data, then we collected into the server for training, and then we deploy, and we deploy a scale. So we used to say that we train once and we deploy everywhere. Once it is deployed, we go for the real world testing, and I don't know you, but let's say what happened to me most of the time, that is not working. So like in this example, you test in the real world and this is not working. And this is actually typical, and the main reason is mainly because of data, let's say most of the time, especially with data-driven approach. Why data? You know that deep neural networks require lots of representative data. So you may have experienced that you collected a few of some data, or let's say you didn't collect in a specific environment. Or, I mean, you were placing the sensor in a different position that with respect to the data were collected. So these are typical examples that I believe everybody experienced and led the final system not to work. Just to give an example, here we were training some sort of object vector for to detect if there were some specific object like the bottles here. So what we did was to use some public data set. In this case was Google Open Images of image of the bottles. But then at the end of the day, the reality is that the sensor that we use was much lower quality. So at the end of the day, the bottle that we were using in the image is this one and not this one anymore. So just to give you a feeling on what happens if you train an object detector only on this data or then fine tune is actually shown in this video here. So on the left, it is trained only on Google Open Images. On the right, it is trained it is fine-tuned using the real-world data. So you can see also from a quality viewpoint that the one on the right is much more accurate than the other on the left. So the question is actually straightforward. So what if? What if the environment now changes again? Or what if you want to change the sensor again? Or, I mean, you want to add new objects, so you have to restart back. So, and you have to restart all of your, let's say, design flow. So on the one side, this is the typical stuff that is done. So you go back, get the data, train, and then deploy. Or, let's say, there are some other machine learning, let's say, approaches where maybe you want to enforce generalization, so you train larger models, and then this can be, let's say, generalized a little bit better to new sort of environment. Let's say, while the one on the left is pretty costly in terms of time, the one on the right is pretty, let's say, against the inference cost. Because in this case, a bigger model will cost you a lot during the inference time. So the question here is that how can we bring instead adaptation mechanism on these kind of devices? Which kind of data, which kind of algorithms, and what is the hardware and software cost? That I will, let's say, especially in these 2 points, we are going to be focused on the next. So here I want to start from an example just to give you a feeling of what continual learning is. So here we have a data set that was collected by a group from University of Bologna, about 50 images. The data set is called Core 50. And basically, a simple image recognition data set. You have to say what is the image, what is the classes among the 50 data set. So in this plot, we have accuracy on the y-axis, and we have time on the x-axis here. So if we do it like normal training at time 0, we train on the full images available, we get an accuracy which is between 60 and 70%. Then, let's say, what if instead we approach this continually? So at the beginning, you provide only few classes, like 10 classes. And then over time 1, you provide 5 new classes. Time 2, you provide other few classes, and so on and so forth. Can we ask our device to learn continually, learn new classes over time? And let's say, basic approach, transfer learning. So you have your new 5 classes at time 1, and you just fine-tune on the new classes. You do the same at time 2, and so on. But what you see here from this plot is that the test accuracy actually remains low. Why? Because of the problem of catastrophic forgetting. Whenever you want to learn a new 5 class, you, let's say, forget the previous one. So this is not working. And that's why, let's say, there is a bunch of work from the community of the continual learning. How can we instead address the catastrophic forgetting and improve the accuracy over time when we have this sort of new data, new classes coming around? So here, let's say, I want to keep the story short. There is a bunch of literature here. Even if the most recent is very recent, so most of the work comes from the last 2-3 years. And here, let's say, what has been discovered is that the most efficient in terms of accuracy approaches are the memory-based. So basically, you have your new data, and you want to adapt your model using backpropagation on this new data. And basically, to not forget the previous one, you use some sort of replay memory in order to preserve some data from the past. So basically, when new data arrives, you combine them with some samples of the previous one, you learn, and then you discard it, okay? And then you update just with few data your replay memory. This is the overall concept, and that's how the same picture of before. You see now the accuracy growing over time, and that's how you can actually address the catastrophic forgetting. Clearly, backpropagation, I mean, it's not a secret. Backpropagation has a huge cost, memory and, let's say, memory and computational cost. But a smart trick on the other side that was actually presented to address this was to use a sort of compromise. And the compromise was called the latent replay. This is a work, again, from another group in the University of Bologna. So we say, let's split the model. We have we have our server. We train it once on some initial data, and then we freeze initially. So we keep the first model frozen here, and then we use just, let's say, an adaptive model, the red one in the slide, that we continuously learning using backpropagation. In this case, the replay memory is not built using previous images, but instead we use some sort of latent embedding so the activation features coming from the latent replay layer, which are much smaller than the image, okay? So here you see in the picture that depending on the position of the latent replay layer, so it can be the last layer or can be one in the middle, on the one side you reduce the memory occupation, that's the pattern size here, of the memory that you need to keep it. But on the other side, you also decrease the accuracy. Let's say you want to retrain only the last layer, you will get a lower accuracy than, let's say, training part of the model. But of course, you reduce the memory and you reduce the time for computation. So now is the question, what is the cost of this training on a MCU? That's what we actually studied in our work. Again, I mean, the message that I want to give is we are not doing training from scratch on MCU. This is absolutely not the case. We want to continually learn new stuff. So there is a new object. We want to learn the new object on top of the previous one. So this is the piece of let's say, the evaluation that and the problem that we are currently addressing here. So here, let's say, without so much fantasy, starting from the memory cost comes from the replay memory. And the replay memory is actually composed by a number of feature vector, which can feature a different size depending on the position where they are in the memory, plus also the bit width. So what we did was to apply some, let's say, concept that for us are pretty common, so quantization. Instead of, let's say, in addition to use it for quantizing the frozen model, we use it also for quantizing the previous, let's say, the previous knowledge. So we use quantization somehow to also to prevent the catastrophic forgetting. And we show here that, let's say, in the table, we compare for different position of the latent replay layer, we compare the accuracy when apply quantization only on the on this memory, or in combining quantization to this memory here and to the frozen stage here. And we see that first of all, the accuracy as it the accuracy is actually decreasing. The accuracy is decreasing when we move to the end of our model. And concerning the quantization, we saw that basically quantizing the latent replay layer, so the latent replay memory, has a larger impact than quantizing the frozen stage. But overall, the quantization actually in this case led us to an accuracy drop of 2-3% that somehow is acceptable with respect to the huge memory saving that we are doing in this case. So overall, what is the memory? So let's say in this plot, we basically plot the test accuracy with respect to the amount of memory that is required. So we took different points, changing the latent replay memory, the number of replay that we had, and also the quantization. And basically, we put in a plot differentiating the different memory. So we can see different region here. So here we have the 4 megabyte region, we have the 32 megabyte region, and 64 or larger than this. So based on it, we identified different clusters, and basically it tells us that somehow if we can be below 4 megabyte, which is compatible with some sort of on-chip memories, we can basically be in a region where we are for this benchmark around 65-70% of accuracy, while progressing more in memory, so using external memories, which can be even SD memories, let's say we can increase the overall accuracy plus percent, okay? So basically what we have here overall is that the more the memory we have, the more the continual learning is effective, but still we can learn something. And here, let's say the plot here break down the memory cost, and we see from this plot that for this continual learning, memory is the bottleneck. This is the, let's say, takeaway message. Not even the gradients, not even the activation, but really this sort of replay memory is the main bottleneck. So for the computation cost, what we did was to deploy some sort of software. So the software is called the Pulp Trainlib, and the software include different primitives to apply learning. So we are used to inference, where we have the forward path between the input and the weights. In addition, here we design and provide multiple layers still for the layer-wise backpropagation to backprop on the weight and the error activation. The code is open source and can be easily applied by using the API. So you compute the forward, then you compute the loss, and then you compute the gradients of the backpropagation. You can apply it depending on the number of layers that you want to backpropagate. Just to go a little bit inside, but not too much, we are used to the fact that for the forward pass, we reshape a convolutional layer into a matmul. So we have input weights for the forward, and thanks to some given transformation, we obtain matmul. Here I'm showing either for a 2D convolution, but also for a convolution of fully connected layers. But this also happens for the other layers. So for the other layers, just changing the tensor, thanks to some other transformation still in the domain of the image to call, we actually reshape it into matrix multiplication. And this gives us the first cost, that now the cost in terms of computation is 3 times larger than was the cost for the standard inference. So now what we did was to, starting from, let's say, we designed these training kernels, starting from a naive matmul. We optimize it using some very standard techniques, so loop rolling and parallelization, and we did our profiling. I'm not sure if I have lots of time, so yeah, I will, let's say, go a little bit.
Yeah, if you can conclude.
Okay, so let's say basically what we have here is that more or less, especially for pointwise layer-like, this sort of, let's say, computation is pretty similar. So we can gain up to, let's say, 4 Mach per cycle, which is 4 times slower than what is basically used for inference, because here we are using floating point mainly arithmetics. To keep it short, we actually did some evaluation of the continual learning scenario that I described before. So basically the evaluation here consists on, we have a new image. I want to learn the new image, so I collect the scenario is that we collect 100 new images. I run the inference on the first part of the frozen stage, and then I do training. Training depending on where I fix the latent replay layer. And here are some numbers on some sort of architecture that I showed before, show that basically, in this case, if you just learn the last layer, this is going to be very fast. Actually, the inference is going to be much faster. As soon as you want to retrain using backpropagation with multiple epochs and multiple iteration, I mean, in this case, you may have a cost of even few minutes. Okay, so it really scale the accuracy there on the final accuracy that you wanna achieve. So I will just jump this, go into the conclusion. So let's say my takeaway here, what I hope to have let's say convey here is that we need some sort of adaptive mechanism, and in this case, we are not pretending to do training from scratch on these tiny devices, but rather to improve what is there. Learn new classes, new domain, and new type of build up on the knowledge. So I show some sort of accuracy versus memory versus latency trade-off on this type of architecture, and see here, already we can do something, especially if we, let's say, are not so pretentious, so we can like retrain the last layers, and but still, I mean, on the other side, the main bottleneck is the memory. So either, let's say, having some new techniques to shrink the memory there will be extremely beneficial, or new approach to, let's say, having some sort of computation, accuracy, proportionality, and then tools, as usual. In order to, let's say, enable this type of stuff, tools are really mandatory. Okay, then let's say, there are some other stuff, but let's say, thanks for the attention. Probably I take too long time.
Thank you.